Hello, in this lesson, I would like to prove two special trig limits. These are the two special trig limits. And we're going to start with the first one. Okay, so let's start with the first one. Okay, so I'm going to move up a little bit. We got some pictures on the side. And I'm going to remove all of these words that I did before, so you can see better of the process of proof. All right, hold on. Yes, okay. So the identity we want to prove is that the limit is that sine theta divided by theta. When we take theta approaches 0, that limit is equals to 1. Okay, to start with, and we like to start with the definition of function. Okay, so we assume theta is between 0 to pi over 2. And in fact, we're trying to prove this limit first. Okay, so we try to prove this limit first where theta approaches 0 from larger than 0. So we first actually consider this limit first. Okay, so the first, we are observing this limit. So that's why it's reasonable to assume that theta is between 0 to pi over 2. Because as theta approaching 0 from larger than 0, and this is the angle that measured from x-axis, and so this angle is theta. This angle is theta. By definition, trig definition, right? On the unit circle, the arch, okay, this arch, okay, if you look at that point, that red dot, this red dot, the arc AB is the same as, so the arc AB is equal to theta. That's just by definition of trig angles. Okay, and for that part, if you have questions about that, you can go back to review trigonometry. But now just take it as a fact, and it is true because this is the unit circle. This is AB. The arc AB is a piece of unit circle. Theta is right there. And also we know that by definition, if you look at the triangle OBC, okay, OBC, this is right triangle, and OB is the hypotenuse, BC is the opposite side. Therefore, BC, okay, BC, we meant this straight line, the length of that straight line. So we use this bar to bar. It's not absolute value. It just means the length, okay? So BC is equals to OB multiply sine theta. Sine theta. That's the opposite side of this angle, which is BC. Since OB is 1, right? It's a unit circle. Therefore, that is equals to sine theta. Okay, so BC is equals to sine theta. All right, and from the diagram, we also see that BC is less than AB. BC here, okay, BC is a straight line. Okay, it's a straight line, it's a vertical line, vertical to OA, and AB. Okay, AB is the line connecting A with B. So between BC if you look at this triangle, right? A, B, C, right? BC is the leg, AB is hypotenuse. So obviously AB is larger than BC. So AB is longer than BC. So the other relationship we're going to have is BC is less than AB. Okay, BC is less than AB. And AB, right? AB, this is straight line between A and B, is shorter than the arc, the curve between AB, right? So that seems to be rather obvious, right? So arc AB. So by this time, we have established a relationship, okay? So what kind of relationship is that? Because arc AB is theta. Arc AB is theta. So now we have, and BC is sine theta. So we're gonna put the substitute of BC here, and we make it is less than arc AB. Arc AB is theta, right? Arc AB is theta. So now we have established a relationship, and this is a useful relationship. And because theta is greater than 0, so if we divide both sides by theta, so in this relationship, if we divide both sides by theta, we got a sine theta divided by theta, and that's going to be less than 1. Okay, so basically we did this, right? We divide both sides by theta, divide both sides by theta. All right, so that's how we got the next step. All right. Okay, so next, now we got sine theta is less, sine theta divided by theta less than 1, right? So we're working on this limit. We're working on this limit. The next paragraph that we want to we are going to look at a bigger triangle. We're going to look at a bigger triangle. Okay, this bigger triangle is ADO. This is the largest triangle. This is the largest triangle. And we're also going to look at BE and EA. Okay, so now we're going to start with, okay, we're still trying to work on this limit, right? But what we're going to do is that we know arc AB, the arc AB, right? You look at the arc AB, it is smaller than BE plus EA. That's obvious, right? So arc AB, okay, I'm going to copy this piece, is less than, right? This blue AB, right? If you look at the red dot here, is smaller than, of course, arc AB is theta, right? Is less than AE plus EB, okay? AE plus EB. So AE plus EB. EB. So that's straight line. In other words, AB, this curve is shorter than the sum of these two straight lines outside. You can see this from the next circle, right? This is the unit circle, this is arc AB and AE, EB, okay? Now continue this journey. We want to establish a relationship between BE and the DE, okay? So now, continue. Okay, we're gonna keep the AE plus. if you compare BE and DE, how is this triangle made? Okay, so from B, we draw a tangent line. Okay, BE is a tangent line passing B. And OB is a straight line. And so there's a straight angle here. So in this triangle, BE and the BD are straight out the legs, and DE is the hypotenuse. The hypotenuse is longer than the leg. So now we're going to substitute EB by the longer line DE. Okay. ED. Okay, so now we got AE plus ED. AE plus ED. So we demonstrated that the arc AB is less than, okay, AE plus ED is AD, right? So this whole sum, this sum is equals to the straight line AD. Okay, so AE plus ED is longer than the blue arc. Okay, the blue arc, which seemed to be rather obvious, right? But we demonstrated, right? And now we look at the triangle ADO. Theta is the opposite and is the angle that opposite to AD. Okay, theta is the angle opposite to AD. And the opposite over the adjacent OA is tangent theta. And therefore, AD is equals to OA, okay, OA multiply tangent theta. So OA multiply tangent theta. Okay, because AD divided by OA is tangent theta. Opposite over adjacent side is tangent theta. So by this time, if you look at the whole of the process, right? And of course, we're going to go one more step further because OA is 1. Okay, so this will be equals to just tangent theta. So we have demonstrated that theta is less than tangent theta. Okay, so we got this piece. Okay, I'm unboxing it. And we also got theta less than tangent theta. Okay, so let's move up a little bit. Okay, so now since we know theta less than tangent theta, and tangent theta is equals to sine theta over cosine theta. So sine theta over cosine theta. With that, okay, what are we going to do? Because everything is in the first quadrant. Okay, theta is the first quadrant between 0 to pi over 2. Okay. And sine theta in the first quadrant is positive. Cosine theta is positive in the first quadrant. So what we like to do is that we're dividing both sides by theta and multiply both sides by cosine theta. And it's still going to be positive. Okay, so basically in this relationship, we're going to multiply both sides by a positive number. And the positive numbers are, we're going to multiply cosine theta. Okay, we're going to multiply cosine theta on both sides. And we're going to divide both sides by theta. Divide by theta. So we multiply the same positive quantity on both sides of this inequality, and it will still be true. And then we simplify it, right? Because theta and theta will reduce, okay? And cosine theta and cosine theta will reduce, and we will end up with cosine theta is less than sine theta over cosine theta, over theta. Okay, so we got the second important relationship. Okay, so we got second. If we combine the first one and the second one, and what would that be? Right? When we combine these two, we got cosine theta over theta less than 1 from the first inequality, and the second one, that's going to be cosine theta less than of sine theta over cosine over theta. Now we created a squeezed situation. Okay, so sine theta over theta is a squeeze in between two other functions. So let's check out the limit. Let's check out the limit. So if we take limits, we're thinking of a squeeze theorem, right? So we take theta approaching 0 on cosine theta, and that's going to be a direct substitution. Is a cosine 0, that's equals to 1. And the limit of 1, of course, is still 1, right? So by squeeze theorem, the limit at theta approaching 0, right? We make it from greater than 0, okay, from larger than 0, sine theta over theta is squeezed in between two limits that are both equal to 1. So this equals to 1. So now by this time, we have proved that this limit is approaching 1 when theta approaching 0 from positive side. Then how about, then of course, naturally, we'll be thinking about this limit that approaching from smaller than 0, right? Limit from left. To do this, to work on this part, okay, we are going to demonstrate, okay, we're going to demonstrate that this function, if I call this a function, okay, f of theta is an even function. Why is an even function? Because if we do f of negative theta, which is sine, that will make it sine of negative theta. And that's going to be equals to, because sine theta itself is odd, right? So that's going to be negative sine theta over negative theta. And that equals to sine theta over theta, right? So that is f of theta. So opposite input produces the same output. Therefore, f of theta is even function. If f of theta is even function, right? When we consider limit, right? So when we consider limit from smaller, we can do a little substitution. We can do a little substitution. In other words, we're going to make a little substitution. We're going to assume, say alpha, okay? Alpha equals to, okay, let me put it this way, okay? Not make it too complicated. Copy, paste, right? If theta approaches 0 from smaller than 1, 0, then negative theta is approaching 0 from larger than 0, right? But if theta approaching 0 from smaller than negative theta approaching 0 from larger than 0. And I'm going to put a negative theta just like that. So you can pretend that this negative theta, which is now approaching 0 from larger than 0, right? So we can think of that as just as a substitution. So negative theta, we can view it as an alpha, and this is an alpha, and this is an alpha. So that's how the substitution works. So at this point, we can use the result we learned here because alpha approaches 0 from larger than 0. So this equals to 1. So at this point, we have demonstrated that limit from right is equals to 1 and limit from left is also equals to 1. Okay, and therefore, right, by the theorem we are so familiar with, on limit from left and limit from right, the limit at theta approaching 0, theta approaching from either side is going to be equals to 1. So this is proved. This is proved. And next, we're going to prove the other identity, other important special limit. Okay, so next we're going to prove this one. Okay, let's see how we're going to do that. Okay. So I'm going to remove all of these things that we've done. Okay, so we start from here. I'm going to just remove what I did before so you can see better this way in terms of proof. So this is what we wanted to work with, right? So in order to do that, we're going to multiply a conjugate of the numerator. The conjugate of the numerator is cosine theta plus 1. So cosine theta plus 1. And they're still equal because we just merely multiply by 1. And next, we use the conjugate property. Denominator multiply denominator. Okay, so this left is 1. Numerator times numerator. So now we know that this is going to be cosine squared theta. Subtract 1 squared. 1 squared is still 1, right? 1 squared is still 1, so we can remove this. And next, what we got is that we know an identity, which is sine squared theta. Sine squared plus cosine squared is 1, right? Sine theta plus cosine squared theta equals to 1. Therefore, cosine squared theta subtract 1, right? So if I subtract sines, if I subtract 1 on both sides, subtract sine squared, I will get cosine squared theta. Right? Subtract 1, that's going to be equals to negative sine squared theta. Okay? All right, so this is the part you're going to just work on the scratch paper. So next step, we're going to substitute the numerator, which is a cosine square theta, by negative sine square theta. Okay, and now what we have is what we're going to do is we're going to put the negative sign in front. Okay, and split sine theta into sine theta multiply sine theta. Okay, sine theta squared is sine theta times sine square theta. And we're going to split this even more. We're going to split this even more. So we're going to split sine theta with over theta, right? So I'm going to set up another fraction. So I'm going to bring this fraction over, right? So one of the sine theta is moved over. This parentheses is going to move over. So basically the same thing, we just moved them around, still multiplying. And we know this limit. When theta approaching 0, this limit equals to 1. When theta approaching 0, right? And this one has a limit because we can just do direct substitution. Denominator is not going to be 0. So this individual limit exists, and this individual limit exists. And so we can use the limit law to, so the next step is going to apply limit law. So we're applying limit law on sine theta over theta, right? So this limit is going to be applied over here. And this other limit will be applied to the other factor, which is right there. Now we can remove that parentheses. We don't really need it. And let's see what we got. Equals to, and there's a -1 because the limit over here is 1, so -1. Multiply direct substitution on that piece, and that's going to be sine of 0, cosine of 0. Cosine 0 equals to 1, so denominator is 2, but the numerator is 0, so the entire product is going to be 0. So by this time, we have proved these other special limit. Okay, so these two limits are considered proved. And what's the use of these two limits? As you can see, if you haven't seen that video, is that these two limits are instrumental in proof the derivative of sine equals to cosine, and the derivative of cosine equals to sine. And we also have some other uses for these two limits. So we're going to have separate set of questions applying these two limits. So this is two very special trig limits. The techniques we used here, such as multiply the conjugate, these techniques is also very, very useful. Okay, as we can see when we see the application of these two limits in our homework questions. Okay, that's all. Thank you for watching.